Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on EMC consideration. Okay, so this video, I'm going to concentrate on conductor emission test and measurement. This video, I'm going to discuss one of the key equipment for conductor emission, which is LISN. Okay, so this LISN actually stands for Line Impedance Stabilization Network. Okay, there are several functions for this LISN, and the function that I'm going to discuss for this video will be impedance stabilization. In short, how can we actually stabilize the impedance? This will be the part 58 series discussion on EMC. So guys, if you're keen to know more about EMC, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on EMC. This is my email. If you have any question regards on this discussion, please drop me an email. Okay? Or if not, I strongly suggest that you ask your question through the comment. Okay, so this is because I hardly check this email. So guys, if you want to have a faster response, ask me through the comment. Okay, before I continue, I'd like to urge you guys to help me by like this channel. When more of you guys actually like this video will have a higher chances to reach up to a larger audience. So guys, help me by like this video. For those who are new to this channel, please consider to subscribe to this channel and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly understand what is the function of LISN, okay, which stands for Line Impedance Stabilization Network, which I have discussed earlier on. Okay, basically LISN is a specialized device that is mainly used in EMC test and measurement to measure the conductor emission from the DUT. Okay, so in short, this LISN is actually an equipment that help to measure the emission that is released by the DUT through the wire, through the conductor wire, for example. Okay, it actually serves critical function. Okay, in short, there are actually three critical functions. This video, I'm going to concentrate on this impedance stabilization. Okay, so LISN actually provide a stable and known impedance. So the keyword is stable and known rather than a fixed impedance. So therefore, from here, you know that okay, the impedance will be stable and the amount or the value of the impedance will be known, okay, to the device under test. Okay, this consistent is necessary, okay, because the impedance of power line can vary, okay, which will otherwise affect the accuracy and repeatability of emission measurement. In short, you can imagine if the impedance of power line actually vary, then therefore we cannot obtain the repeatability of the conductor emission measurement. Okay, because if the power line is changed from test house to test house, all of them actually has different impedance, let's say, okay, and therefore the measurement result will be inconsistent. So because of this, we need to ensure that the impedance of the power line need to be stable and known, and therefore with this, the different test house can have the same effect through the LISN, which means that the result will be accurate and most important, it can be repeatability. Okay, beside impedance stabilization, okay, LISN actually provide noise isolation. Okay, it actually isolate the DUT from external noise present on the power line. Okay, ensure that only the emission from the DUT are actually measured. Okay, beside that, also noise coupling. Okay, LISN actually couple the conducted noise emission from the DUT to the measuring equipment. Okay, either we use the EMI receiver or spectrum analyzer. Okay, while the LISN also block the noise from the power source. Basically, this will be the function of LISN. Okay, so in order to conduct emission, okay, you can easily connect them as shown in this diagram. Okay, it is definitely possible to measure the conductor emission produced by the DUT using this simple setup. Okay, over here you can see that this will be the EUT. Okay, as let's say this is the power supply to turn on the DUT. And therefore, this power supply will be the source to turn on the DUT, and I can actually measure the emission from the DUT. And basically, this will be a very simple setup to measure the conductor emission produced by the DUT. Okay, however, okay, the amplitude of the conductor emission will be influenced by the impedance of the source. Okay, from here, you can see that the impedance, okay, on the power supply will also affect the credibility of the test and measurement result. Okay, the source impedance is part of a voltage divider in the overall system and has a significant influence on the amplitude of the measured amplitude of the conductor emission. Okay, basically this impedance of the power supply, they actually serve as a so-called impedance from the overall system, and therefore, okay, the result of the conductor emission is actually affected, as it is necessary to get the same result from the EUT in any NAP anywhere. It is necessary to remove the impedance of the supply source from the equation. Okay, in short, over here, you can just imagine, okay, different test house have different power supply. And once you have different power supply, you can actually have potentially different impedance. From this diagram, you can see that your DUT, okay, and this power supply, they are actually connected in parallel. In short, okay, the impedance of the power supply will going to affect the overall, okay, the impedance that is seen by this spectrum analyzer. In short, because of this, then you will not be able to get the same test and measurement result, because as I mentioned earlier on, different test house have different power supply and therefore different impedance, and therefore you will actually obtain different result from the emission from the DUT. Let's say the emission is still the same, okay, but because of the different impedance, okay, so therefore the measurement actually vary. And because of this, then the result that you actually do from test house to test house, they may not be consistent. And in order to make it consistent, okay, we actually can add in a LISN. Okay, they basically will be incorporated into the setup to provide a defined impedance for the conductor emission traveling on the supply lines of equipment under test. Okay, so now you can see that it's slightly different over here. Okay, so this part here I will explain, okay, on the next few slides. But over here you can see that I actually insert a LISN in between the power supply and your DUT. And this LISN actually also has a port to send it to the spectrum analyzer for the test and measurement over here. Okay, a LISN can be connected to any power supply and provide the same voltage and current. Okay, so the key thing is the same voltage and current capabilities as the power supply at the EUT termination. Okay, the source impedance of the LISN is specified by the EMC standard. Okay, ensure repeatable conductor emission measurement in any laboratory. Okay, so in short here, you can see that the source impedance of the LISN, okay, the source of the LISN is basically specified by EMC standard. Okay, so this will ensure that the result will be consistent, okay, which I'm going to further discuss on this. Okay, a typical LISN consists of several key components. Okay, you can see that this is a LISN. Okay, you can see that it actually makes up of inductor, capacitor, and resistor. Okay, let's go through them. Okay, inductors, okay, these are used to present a high impedance to high frequency noise. Ensure that the noise is direct towards the measurement equipment instead of back onto the power supply. Okay, so let's do this. Okay, for example, the key purpose of this measurement, okay, is basically to measure the emission from the DUT, for example. Okay, basically you can see that the disturbance, okay, from the DUT is actually released from the cable, and they basically will be propagate along here. So what happened here is basically we need to put an inductor over here. So when the frequency is high, okay, this value or the impedance will be also high because of this equation. From here you can see that when frequency is high, the impedance also will be high. So therefore, when this is actually conducted at high frequency, okay, this will be act as a high impedance, and therefore the signal will reluctant to flow this path, and hence they will flow over here, and basically the emission from the DUT will be measured by the spectrum analyzer or EMI receiver. Okay, so basically this is the role of an inductor. They present a high impedance to high frequency noise, ensure that the noise is direct towards the test and measurement equipment instead of back onto the power supply. In short, your EUT noise, they basically release from this path, and because of this high frequency, this become a high impedance, and therefore the source of the noise will be reluctant to flow back to the power supply, and hence the source of the DUT basically will flow through this path, and hence will be measured by the test and measurement equipment. Okay, as for capacitor, okay, they are mainly employed, okay, so basically to bypass high frequency noise to ground. Okay, just imagine this. For example, okay, some of the signal actually manage to penetrate through the impedance, and this, when the frequency is high, this will become small, and this will become like a short circuit. So in short, the noise will be shorted to the ground. Basically, this will be known as a bypass capacitor. So basically, these capacitors are mainly to bypass high frequency noise to the ground. As for resistor, they are actually help in defining the impedance and ensure stability, okay, which I'm going to explain later on. Okay, but the resistor doesn't play much role. Mainly in the LISN, the role will be played by this inductor and also the capacitor, okay, which I'm going to further discuss on these few slides here. Okay, so for LISN, you actually have two types of LISN. Okay, one we call the inductor with 5 microhenry. Another one is actually a 50 microhenry. Okay, which one to use? Okay, I'm going to explain. Okay, these 5 microhenry LISN are primarily used for testing equipment that is installed in vehicle or automotive. Okay, in short, basically 5 microhenry impedance, 5 microhenry inductor is mainly used for automotive standard. Okay, because this 5 microhenry inductor actually simulate the supply line with a length of 5 meters. Okay, as wiring harness in vehicle rarely exceed this length. Okay, so in short, for vehicle, the length of the cable is hardly that long, typically 5 meters. And because of this, okay, you can see that the inductor value is actually smaller as compared to the 50 microhenry, which I'm going to further discuss. So in short, these 5 microhenry are mainly to use in the test and measurement in the vehicle standard. Okay, so this is what I mean. Okay, 5 microhenry inductor actually simulate the supply line with a length of 5 meters. As the wire or maybe as the cable in the vehicle, they hardly exceed this length. These LISN are primarily used for conducted noise measurement in the frequency range of 150 kHz to 110 MHz. Okay, 5 microhenry LISN designed for testing according to D0160 standard and also MU standard 461. Okay, covering the frequency range of 10 kHz to 400 MHz. Okay, so this is more on a commercial standard here. On the other hand, 50 microhenry LISN are primarily used for equipment installed in domestic or industry environment. Okay, the 50 microhenry inductors simulate 50 meters of supply wiring inside a building. Okay, so in short, for those devices that we use in domestic or industry, they are typically longer as compared to the 5 microhenry with a length of 5 meters. Basically, if for 50 microhenry, okay, basically we are actually trying to simulate like a 50-meter cables inside, mainly used inside a domestic or industry environment. So basically, in short, okay, if you are going to use this for vehicle, okay, then you need to use this 5 microhenry inductor as a LISN. So if you want to do most of the testing for the commercial product, for this case here, then you need to choose the 50 microhenry inductor. Okay, basically the key thing is the length of the wire. They basically, for this case here, 5 microhenry is for short wire, 50 microhenry is mainly for a longer wire that is mainly for domestic and also industry environment. Okay, so before I continue, again, guys, urge you to help this channel by like this video. If you had learned something from this video, please consider to subscribe to this channel and turn on your notification bell. So let's continue. Okay, so let me explain, okay, in short, okay, how this inductor and also the capacitor play the role to ensure a stable impedance at frequency above 5 megahertz, which means high frequency. Okay, when the frequency is high, okay, so over here, when frequency is high, this impedance will be high. When frequency is high, this impedance of this capacitor will be small. Okay, because the higher the frequency, the impedance will become smaller. Over here, the impedance, or sorry, the frequency is higher, then the impedance will also be higher. So this case here, we are going to consider frequency above 5 megahertz. Okay, the impedance of the 5 microhenry inductor is high, as I explained earlier on. The LISN impedance at the EUT is dominated by the 50 ohm load impedance. Okay, so how this is possible? Okay, in fact, when the LISN is used for conductor noise measurement, the 50 ohm impedance is actually the input impedance of the connected spectrum analyzer or EMI receiver. Okay, let me explain. Okay, most of the time here, this is where we put our measuring device, whether is it spectrum analyzer or EMI receiver. Okay, they have an input impedance of 50 ohm. Okay, when we actually put these two things in parallel, 50 ohm in parallel with 1000 ohm, okay, if you know that anything that we connect in parallel, okay, we can actually simulate that it's actually about 50 ohm. Okay, because when they are actually parallel, it will be always take the so-called the smaller impedance value. So over here, when these two impedance they are actually parallel, I can assume that this is actually 50 ohm. As I mentioned earlier on, for high frequency, okay, for this case here, for high frequency, this will be high. Okay, as for this part here, when this is high frequency, this will be small. So this behave like a short circuit, and they don't play any role on the impedance to make things easy for discussion. I assume this will be a short circuit, and therefore over here, you can again imagine that it will be a 50 ohm. And for this case here, if this is high frequency, okay, this will be a high impedance. And when high impedance again in parallel with 50 ohm, then 50 ohm will be dominate. And therefore, for this case here, from the EUT direction here, you can imagine that it will be most like a 50 ohm impedance. Okay, so I will explain this is not really exactly 50 ohm. Okay, I will explain okay what will be the value of this here. But over here you can see that the key idea is for the DUT at high frequency, when I actually look over here, it must be like almost 50 ohm. Okay, so which is possible okay by making use of these inductors and also capacitor playing at different frequency. For this consideration is on high frequency, which I have explained over here. Okay, this also explains why the RF output of a LISN has to be terminated with 50 ohm when used without measurement equipment connected. Okay, let's discuss on another frequency which is below 5 megahertz. Okay, once it's below 5 megahertz, which means that this impedance is not that big anymore. And basically, when this is small, this can be quite significant. Okay, so basically what will happen at frequency below 5 megahertz, the impedance of the inductor combined with the 1 microfarad capacitor start loading the 50 ohm resistor. Okay, so basically, like I mentioned earlier on, this start to increase. Okay, so basically the value of the impedance start to increase. This start to reduce. Okay, when at low frequency, this may not be that large. This can be quite significant. Okay, and then the role of this inductor and capacitor, okay, will be start to load the 50 ohm resistor, which means that the value may not be exactly 50 ohm anymore. In fact, if you really understand this, when this is actually small, okay, this may be the dominant factor. As I mentioned earlier on, for circuit that is connected in parallel, the smaller impedance actually will be dominant. And because of this case here, this can be the dominant factor, okay, which I'm going to explain on the next page here. At frequency below 5 megahertz, the impedance of the inductor, okay, as I mentioned, combined with the 1 microfarad capacitor, they start loading the 50 ohm resistor, and the overall LISN impedance decrease according to the specific impedance curve. Okay, let me explain on the next slides. Okay, so basically on the next slides here, okay, basically will be the impedance curve. Okay, basically mainly for a 5 microhenry LISN basically from the CISPR 25 standard at the NXC. Okay, so basically this is the impedance from the LISN, okay, for a 5 microhenry LISN over here. Okay, as I mentioned earlier on, okay, let's from this 5 megahertz here, okay, you can see that, okay, it's not really that constant, but again, you can imagine that they are almost very close to 50 ohm. Okay, not exactly 50 ohm, but close to 50 ohm. As I explained earlier on, when the frequency is high, what will happen? Okay, when the frequency is high, this will be high, this will be small, and will be treated like a short circuit. And this 50 ohm in parallel is almost like a 50 ohm, and this is high impedance, and therefore this is almost like a 50 ohm. Okay, but definitely will not be exactly 50 ohm, will be slightly less than 50 ohm, and therefore, okay, this case here, for anything that is above 5 megahertz, you can see that they are almost 50 ohms, but not really 50 ohms. Okay, so another consideration is when the frequency is low. Remember, I have also discussed on this, when the frequency is actually below 5 megahertz, okay, because this inductor may not be that big anymore, and it can be quite small. And once this inductor is actually smaller, as you can see from here, basically this part here will be dominated by the inductor, okay, impedance, and then after that, the effect start to lesser. Okay, so basically over here, you can see that when the frequency is low, mainly will be controlled by the inductor. Okay, so this capacitor will also play some role. Okay, remember at the very low frequency, okay, basically this value, okay, will have some significant. This is small, and this will have some significant value. And together, okay, the inductor and also the capacitor will ensure the impedance of the LISN will be making this standard as illustrated by CISPR 25 for 5 microhenry LISN. Okay, so basically this is what I have to discuss on LISN. I think I actually have more discussion on LISN. So guys, if you want to know more about LISN, okay, please let me know by like this video. Okay, when there are more likes, then I will continue the discussion on LISN. Okay, if not, okay, I will actually prefer to further discuss on the rest of the EMC discussion. Okay, so guys, if you're keen to know more about LISN, okay, for example, there are three different topology for LISN, and also some of the so-called noise decoupling, etc. So if you're keen to know more on this, okay, please let me know by like this video. Okay, so that's all I have for this video. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.